Hello, I'm Saurus Vidya from Engineering Physics Department. I would be working with movie recommendation systems based on collaborative filtering. Broadly speaking, there are three recommendation methods. Collaborative filtering, which is just a technique that predicts user preferences for items. For me, it was movies based on the preferences of similar users. In the context of user movie database, this technique involves predicting how a user would rate an unwatched movie based on the ratings given by top 10 or top 20 similar users. These threshold can be changed. Then I have taken my dataset from the Netflix price, which contains five files: combined text 1, combined text 2, combined text 4, and movie titles, which movie titles basically contains name of the movie corresponding to a particular movie ID. Our dataset is initially containing a movie ID, then column user ID, the rating which the user has given to the movie, and on what date the user has given the ratings. Date is of the format year, then month, then date. I started with importing important libraries, combined the data, and separated out it in user column, movie ID column, and rating column. This was the thing I got, and later I sorted my data as increasing order of time for dates. Then check whether are there one values or duplicate values present in my data. How in a day I found that I had almost 100 million plus ratings from 480k different users between the time 1998 to 2005. Then I created my sorted data.csv into 8:2 ratio for training and testing purposes. Then I performed video on trade data and testing data. On average, the rating score given by this number of users, the rating stay given by this number of users, and the minimum rating the users have given by one to all to bunch of your movies. I did a day of the week to check whether users are biased towards a particular day of the week or not. Found none. None. No, it's not happening. Then I plotted the graph of number of rated movies per user and found that by considering quantiles. Quantiles are basically the values that split sorted data probability distribution into equal parts. Uh, let's say 0.03 quantile divides sorted data into few parts. Quantiles are also used to check the shape of distribution, and I found out that there are less than 10% of movies which are rated by a large number of users, whereas majority of users have rated only a few hundreds of movies. But uh, while moving ahead, I the present data which I had was distributed in four columns, which takes a lot of memory because there are around 100 million plus rows. To minimize usage of memory, I am creating two separate arrays for movies and one for users, which is called sparse matrices. I have created one for training dataset, then created one for testing dataset, and calculated their sparsity, which was good enough. Calculated average global rating per movie and per user, which I will use for machine learning purposes. Made PDF and CDF for training the dataset and applied the same things on testing dataset. Then started computing similarity user similarity matrix for getting the top 10 recommendations for similar users. But initially, when I started with all the users, it was taking a lot of time. Then switched to 100 users, which also took a lot of time. Then I computed it for top 200 users and find it out top 100 similar users for each. This still took me 9 minutes. So I asked with 17k dimension, of course. I haven't removed any of the dimension. So I computed it. How much time will it take when I applied for the whole dataset? I found out it will take 12.93 days, which is a huge time and compute power. So I switched to truncated single value decomposition method and I applied the same thing for 100 components for and the method I used was algorithm. So I got explained variance ratio to be decreasing and decreasing and decreasing. Even for 100 components, it took almost 18 to 20 components. Oh, sorry, 80 to 85 components to go from 36 to 0.46. So I estimated to get a good accuracy, we need at least 60% of explained gain in explained variance. So it will take around 400 to 500 plus components, which is also a useless method for user-user similarity calculations. Then I started with computing truncated user-user metrics, which which was for 50 users, which also took a huge time, 4 days approx. No doubt the time which involved has decreased, but 4 day plus time is also very long. I found out few glitches or drawbacks in this method. I was calculating user-user similarity for the suppose I have calculated similarity for user one and user two. Then the code was again running for calculating similarity for user two and user one. This could be eradicated if I just compute for upper triangular or either lower triangular matrix, but roughly the time would get half, 2 days, which is also a lot. So I these are the drawbacks which I have mentioned. So I switched to movie collaborative filter, which didn't took a lot of time. It was completed in within 15 seconds. This this code just takes a movie ID as an input and gives top 10 recommendation. I'm using movie titles to print movie names as well, along with movie IDs. I have chosen 1061. Then it turns out 1061 corresponds to this movie. There are this much ratings, etc. The top 10 recommendations are here. This is very uh, consuming time in running. So I have just built a Streamlit interface to resolve this. I am just running it and entering my movie ID, and it gives me top 10 recommendations for the entered movie ID. And it also checks about the recommendations are correct or not via calling Google API key. The movie ID corresponding to movie name is on my GitHub. It is basically movie titles.csv. This is movie released year, movie ID, and this is movie name. My recommendation is running. Till we move ahead to movie recommendations. Here the now the same approach we use can be applied for user similarity too, but it will not be applied for to whole users. We can just print top 10 users. Uh, to combine both, uh, above one was just checking the movie ID and giving top 10 movie recommendations. But we need movies, top 10 movies for a particular user who has watched a given movie ID. So I started with machine learning algorithms. Basically, what I have done is I have used Surprise Library. Surprise Library uses featureizing data, refers to the process of converting data into a format that can be used by the recommendation algorithms implemented in Surprise. Surprise provides various algorithms for collaborative filtering and recommendation. And I have used matrix factorization, particularly single value decomposition (SVD). This algorithm typically expects the input data to be in specific format, like I have featured user movie interaction data, basically ratings in a featureized data, by which consists of a matrix where rows represent users, column represents items. In this case, movies and the values represent the ratings. So I started with loading the data. I considered only a small data set because it is around 100 million plus ratings, which was taking a lot of time for computation. So I have made small test data set and small training data set. and featurized how much ratings they have. Then filtered out the top five user and top five movies for each user and movie table, and then converted the data into appropriate data structure read by surprise, whether it is data set or reader object. This code is just doing the same, and I have made this regression train.csv which contains top five movies and top five users. It has 78751 user movie pulse, and this code block is finding out those things which took around me 3 hours, 30 minutes to get it computed. In the same way, I featured the small sample data for regression via XGBoost and declared two tuples, a tuple for storing the algorithms which I will use further to storing their RMSE and MFE for comparison purposes. What basically I have done is applying many algorithms and took their RMSE via XGBoost and RMSE. Initially, I started with XGBoost, taking 13 features, surprise baseline predictor, then passing on the features to XGBoost, then again taking XGBoost, then again taking surprise library with KNNs and passing it to XGBoost regressor. Then I used surprise KNN model with movie similarity and surprise KNN model with user similarity and passed on it to XGBoost regressor after featurizing it to RMSE, then used SVD and SVD plus and passed it to XGBoost regressor and passed later the whole thing to XGBoost regressor and calculated their RMSE. SVD plus is basically an extension of traditional SVD design to address some of its limitations, particularly with regard to handling implicit feedback and improving recommendation quality. In addition to considering explicit movie user interaction, which is basically ratings, SVD Plus takes into account implicit feedback such as movie reviews or number of minutes time watch. It achieves this by incorporating a user-specific bias term and a movie-specific bias term into the factorization model by considering both explicit and implicit feedbacks. SVD++ aims to provide more accurate recommendations than SVD, as it is just a mathematical term of U sigma and V transpose. Later, I've compared all of those RMSE and found out that SVD has the lowest RMSE, which is indeed good, and compared it to SOTA, which Netflix used that time, sign match, which is given in this research paper. The RMSE which Netflix had was 0.95 before competition, and after competition it was 0.85, and my was 1.08, which is 13% error approximately from the sign match. But it was because of I trained my model on 88,000 users for 800 movies, and my testing data set was of 4,000 users and 400 movies. This, but shortening our sample won't create much disparity. Then by using SVD model, I have taken a user ID and a movie ID and gave the top 10 recommendations of movies which user haven't watched and the predicted rating which user might give to these movies based on SVD++ and SVD algorithm. This is my report on strategies which tells how to reduce hallucination and instability. Our instability is basically a RAG-based LLM model, and the LLM RAG-based LLM pipeline is shown here. We have some documents, converted them into chunks with minimum overlap, converted these chunks into numbers, and not necessarily 0 and 1 always. Then converted those into embeddings and converted into vector database and made the conversational pipeline. Then InstaGPT hallucinates when it takes or refers to top 5, top 10 Google searches when it doesn't found any response to query in the retrieved data or trained data, and there it starts hallucinating. The top 5, 10 Google searches are not always correct. They may have some garbage behind them. The basic strategy is to use thread of thought, which is inspired by human conjunctive process, where we use query optimization and analyze extended context. Basically, we do prompt engineering in this for large data sets, which is indeed a problem with InstaGPT. We need to maintain high quality embeddings. The same thing is done by BERT and GPT. They use continuous embedding vectors, which have infinite range of values with specified dimension. For like BERT has around 760 plus dimensions. These continuity results in certain fuzziness sometimes or errors, allowing context sensitive interpretation of word meanings. So we need high quality embeddings for sure to retrieve or to extract good quality of embeddings. We can have pre-existing methods to retrieve those as per our purposes. Then we can also employ certified embedding search, which is basically converting each existing embeddings into 2 or 3 more embeddings. Then we can implement a thresholding system, which is basically when we retrieve the chunks, the top 10 chunks get shortlisted. But it is always possible that the chunk which is of our interest isn't shortlisted. No doubt we can go through chunk relisting, but the if our interest chunk is not in the retrieve list, how it will get relisted? So we can have a thresholding system where model itself learns to select top n chunks itself, where which means n would be variable as per the context of the query and how large is the data set it is targeting. And even if it doesn't count, it can simply say, sorry, I am unable to answer your query. Chunk listed, chunk relisting can also help to relist the chunks as per their preference and prioritize order once they are retrieved. If we are working with large data set and our InstaGPT uses ITC container, we have storage problems. So we can pre-process our trained data and summarize it and then feed it into our models. The summarization methods and models do exist already. Then we can have changes in context window. Even rather than sending each query and its response back to the context window, we can have a separate standalone question to be sent to the context window, which would reduce space and would reduce memory usages. And this approach reduces hallucinations significantly, creating knowledge graphs. We can integrate a graph database management system like Neo4j parallelly with traditional vector, vector databases. And we can also set up this Neo4j method to respond to query which are mainly focused on problematic question, and it will not retrieve any information from vector databases, as graph database management system is more efficient than traditional method. Beside knowledge graph usages, we can have parallel search operation across multiple processing units or nodes to improve scalability and performance. Again, the models and methods already exist for this too. We should not be over dependent on the retrieve documents, because when retrieving documents featuring the data might conflict. For example, for me, it shows 4 year BS chemistry as my department, but my current department is engineering physics. There might be a conflict in the data set feed into it, which is a hallucinated problem. We can use metadata to track the location of chunks, which is basically labeling our trained data. But if our data set is too large, how would we do that? We can use original pre-existing models as per our use case, or we can have a human annotations where we will label some of the data and use machine learning algorithms to scale it to the whole data. Another thing is RHFL, response hierarchy with feedback loop. This involves taking a user feedback driven approach for refining the capability of chatbots, which ChatGPT uses, and model utilizes this feedback to identify and rectify errors and its training data and generating algorithms, thereby enhancing the accuracy and reliability of its responses. By analyzing the user's responses, it can also uh, get we can all the user can also get personalized responses. Then we had mixture of experts MOE, which is basically integrating not many, few few agents to check each other progress, which may help in reducing hallucination and correct mistakes. Where and this facilitate a robust, fast, and fact-checking mechanism. We can also incorporate a discriminator, where InstaGPT will serve as a generator and aims to produce coherent responses to users, whereas a hallucinating detector such as discriminator can be accessed to check the accuracy of InstaGPT response, which is basically same as RHFL, but instead of taking user feedback, we are taking feedback from a discriminator. The main issue is continuous data uploading. Our model should be uploaded because the users parameters keep on changing daily. And if our model's data will not change, then accuracy will surely decrease. We can incorporate online learning, catching mechanism, data sampling, filtering mechanism, and instead of processing data in real time, we can process it in low traffic times, etc. There are many approaches, all listed there. Then RAG versus fine tuning. Fine tuning, according to me, fine tuning is not appropriate for the InstaGPT. Rather, RAG is good enough because fine tuning increases the cost and it's not good for poorly curated data because we need top notch data for fine tuning. And for InstaGPT case, it's not possible because of bureaucracy. So, cost management and resource allocation involves some math I have done here to calculate the total amount that InstaGPT much minimum requires to run. I have considered a virtual machine because we do not have our own container and ITC container is rapidly filling. So the data available on the net, I have taken and calculated as according to it. Supposing that our Instant GPT runs every hour on every day in a month, which gives us 720 hours. So the the amount to compute resources would be 2600. The data storage, which I broadly understand, is of 13 to 17 trained PDFs, which we are using, which I guess are not more than 50 text pages each, which will incur us amount of 170 rupees per month. And model deployment is a heavy cost. Our Gymkhana servers are almost similar to Azure services, which also uses the container system. So it would range around 6,000 rupees and total costing would be around 8,700. But I might consider some errors and fluctuations. The total costing for a month for InstaGPT would be 10,000, and here are some references which I used.